In the first half of 6.6, we looked at how to solve equations when they are exponential equations, which meant that the variable was in the exponent. This time we're going to look at how we can solve equations when they are logarithmic equations, which means we're also going to have to look at if we can rewrite them as exponents in order to solve them. So one of the things we need to keep in mind is logarithmic equations sometimes have extraneous solutions, and we need to think about when a logarithmic equation would have an extraneous solution. And essentially it would be an extraneous solution if you ended up where you were taking the log or natural log of a number. For like instance, the log of x equals something, and you ended up with x equals -5. Well, we can't take the log of a negative number, so that would be an extraneous solution. And we'll get to a couple of those examples here shortly. Let's go back for just a second. So let's actually look at this property of logarithmic equations. Basically, if you're taking the log with the same base and you have the log with the same base on both sides, then what you're taking the log of is equal to each other, which means if you look up here in this example, log base 2 of x equals log base 2 of 7, log base 2 and log base 2, you have the same log of the same base, which means x would equal 7. So what that actually looks like is letter A here. We have the natural log, also is the same property for natural logs. The natural log of 4x minus 7 equals the natural log of x plus 5. Well, you have the natural log on both sides, which means if you're taking the natural log of 4x minus 7 and the natural log of x plus 5, that means that 4x minus 7 equals x plus 5. So all we have to do is we have to solve for x, and we get 3x minus 7 equals 5. If we add 7 to both sides, we get 3x equals 12, and x equals 4. And what I meant by extraneous solutions, we just need to go back and double check. If we put 4 back in for x in either one of these, we just have to make sure we don't get a negative number. 4 times 4 is 16, 16 minus 7 is positive. 4 plus 5 is 9, 9 is positive, so that's fine. Okay, and then if you look at letter B, it's a little bit different. Okay, if you notice, there is not a log base 2 on the right-hand side of that equation. We have log base 2 of 5x minus 17 equals just 3. Well, if we have a situation like that where we do not have a log on both sides of the equation, that means we just need to change it into exponential form. So if we have log base 2 of 5x minus 17 equals 3, if we rewrite that as an exponential form, we'd have 2, so we'd have a base of 2, 2 to the third power equals 5x minus 17, and then we just need to solve for x. 2 to the third is 8 equals 5x minus 17. If we add 17 to both sides, we get 25 equals 5x, and x equals 5. So that's the two basic type of equations we're going to start looking at. Okay, if you notice I have a line drawn down the middle of this slide, it's because the ones on the left, okay, A and C, A has the natural log of 4x minus 7 and the natural log of x plus 11. That means we can just set those parts equal to each other. Letter C right below it has the log base 2 of 3x minus 4 and the log base 2 of 5. It has log base 2 on both sides, which means we can just set those two parts equal to each other. If you notice on the right-hand side, you have log base 2 of 4x plus 8 equals 5. Well, we don't have a log base 2 on the right-hand side, which means we're going to need to change that into exponential form. Same thing with letter D right below it. So let's go ahead and look at how we'd actually do that. If we have the natural log of 4x minus 7 equals the natural log of x plus 11, again, we have natural log on both sides. We're taking the natural log of two things, which means those will be equal to each other. 4x minus 7 equals x plus 11. If we subtract x from both sides, we get 3x minus 7 equals 11. If we add 7 to both sides, 3x equals 18. X equals 6. And again, we can go back up and just double check to make sure that when we put 6 in for x in both of those natural logs, we don't get a negative number, and we don't. Letter C right down below there, log base 2 of 3x minus 4 and log base 2 of 5. So we have a log base 2 on both sides, which means we can just set those two parts equal to each other. So we would have 3x minus 4 equals 5. If we add 4 to both sides, we get 3x equals 9, and x equals 3. Again, we can go back and just double check. We're not going to put x in on the right-hand side, but if we put x in on the left, 3 times 3 is 9, 9 minus 4 is 5, so we're good. On the right-hand side, notice again, it's a little bit different. You do not have a log or a natural log on both sides of the equation. If that is the case, then you need to change it from log form to exponent form. So on letter B here, we have log base 2 of 4x plus 8 equals 5. Okay, if we change that, we have our base is 2 to the 5th power equals 4x plus 8. 2 to the 5th power is 32 equals 4x plus 8. If I subtract 8 from both sides, I get 24 equals 4x, and x equals 6. Again, down on the bottom, I have a log on the left. I do not have a log on the right, which means I'm going to need to change it into exponent form. So I'm going to have 7 to the 2nd power equals 4x plus 9. 7 to the 2nd power is 49 equals 4x plus 9. If I subtract 9, 40 equals 4x, x equals 10. Again, so just so you can kind of see the difference between the two. The ones on the left have a log or natural log with the same base on both sides of the equation. The questions on the right only have a log on one side, and then which means you're going to have to change it into exponent form. Okay, so we're going to take some things that we've already learned and we have already done, and we are going to apply that to solving this equation. So we have the log of 2x plus the log of x minus 5 equals 2. Well, if you think back the other day when we had a plus sign in between, that basically meant if you had the log of 2x plus the log of x minus 5, in order to condense those or put them back together, that means you're multiplying those two parts together, which means we're still staying in log form. So we'd have log, and we're going to multiply those two blue highlights together, of 2x times x minus 5 equals 2. In that step, all we did was we took the two terms that were being added together and condensed them back together using our properties of logs from the other day. Then I'm just going to multiply that 2x through, and I'm going to get the log of 2x squared minus 10x. Again, all I did was I multiplied that 2x all the way through, equals 2. Again, not to forget, if there is no base, it's a base 10. Now we have an equation kind of like what we just did a minute ago, where we have a log on the left and not on the right, which means we need to change it to exponent form. So we'd have 10 to the 2nd power equals 2x squared minus 10x. Now we're just going to solve it like we did all of first semester, where we have a quadratic equation here. We're going to end up factoring it all the way out. So we'd have 10 squared is 100 equals 2x squared minus 10x. Anytime we have a quadratic, which means it's a squared, we need to get it set equal to 0. So I'm going to subtract 100 from both sides, and I get 0 equals 2x squared minus 10x minus 100. I'm looking to factor this. First thing I look for is a greatest common factor. I'm going to take a 2 out, and I have x squared minus 5x minus 50. Now I just need to factor that apart. I need a factor pair of 50 that adds together to be negative 5. So I have x and x. If I'm thinking on that terms, I have 10 and 5. So I need to have a negative 10 and a plus 5. When I set those each equal to 0, I get that 2. Again, if you divide out the 2, it's basically gone. You have 0 equals x minus 10 times x plus 5. Set each one of those equal to 0. if x minus 10 equals 0, that means, equals 0, that means x equals 10. If x plus 5 equals 0, that means x equals negative 5. And this is where it's important, where we go back to the original equation and remember that we cannot take the log of a negative number. So if we had that x was 10, if we go back all the way up to the top up here, if we put 10 in for x, we'd have the log of 2 times 10. 2 times 10 is positive 20, plus the log of x minus 5. 10 minus 5 is 5. But notice when we put negative 5 in for x, we get the log of 2 times negative 5, which is the log of negative 10. And we can't take the log of a negative number, which means negative 5 is going to be extraneous, and positive 10 is our only solution. So here we have, again, just some more examples of what we've been doing in this second part of this section. Okay, I have the natural log and the natural log on both sides, which means we're going back to the simpler problems where we can just set 7x minus 4 equal to 2x plus 10. And when we solve for x, we subtract 2x from both sides, add 4. We end up at x equals 3. Okay, if you notice, looking at question number 6, we have a log base 2 on the left, we have no log on the right, and there's no terms being added together like on the questions on the bottom half of the slide, which means we can just take it and put it directly into exponent form. So we'd have 2 to the 5th equals x minus 6. 2 to the 5th, again, is 32, equals x minus 6. If we add 6 to both sides, we get x equals 38. Okay, so now we're getting into some questions again that were a little bit harder. Again, I know when I have to condense them because I have 2 logs on the same side that are being added or subtracted. So if I look, I have log of 5x plus log of x minus 1. That plus sign in between there tells me I can put them together to be the log of 5x times x minus 1 equals 2. We're going to go through that process again. I'm going to distribute that 5x, so I'm going to have log of 5x squared minus 5x equals 2. Once I have it written in that form, keeping in mind if there's no base, it's a base 10, I can rewrite it as an exponent, so I'd have 10 squared equals 5x squared minus 5x. Again, it's an exponent, or excuse me, a quadratic because it has a squared. So I'm going to go ahead and get it set equal to 0. I just did 10 squared is 100. If I subtract 100 from both sides, I get 0 equals, there should have been a squared there, 5x squared minus 5x minus 100. Again, I need to take out the greatest common factor. Of 0 equals 5 times x squared minus x minus 20. If I divide out that 5, I'm just left with x squared minus x minus 20. So I'd have 0 equals, I'm going to factor that to x minus 5 and x plus 4, which means my 2 solutions are either x equals positive 5 or x equals negative 4. And when I go back to my original equation, if I have x equals 5, putting 5 in for x is fine, but when I put negative 4 in for x, I get the log of a negative number, which means 4 is extraneous and x equals 5 is my only solution. Okay, so let's take a look at another one. These are just some more examples of the exact same kind of problem. Log base 4 of x plus 12 plus log base 4 of x equals 3, which means using that property that if they're added together, condense them by multiplication, I'd have log base 4 of x times x plus 12 equals 3. So I'd have log base 4 of x squared plus 12x equals 3. If I rewrite that as in exponent form, I'd have 4 to the third power equals x squared plus 12x. 4 to the third power is 64 equals x squared plus 12x. I need to get set equal to 0, so if I subtract 64 from both sides, I get 0 equals x squared plus 12x minus 64. So I need a factor pair that adds together to be 12 and multiplies together to be negative 64. That would be x plus 16 and x minus 4, which means my two solutions would be x equals negative 16 and x equals positive 4. Going back up to my original equation, I cannot have the log of a negative number, so x equals 4 is my only solution. Number 9 looks like the same basic idea here, so I'm going to have log base 2 of x times x minus 2 equals 3. Log base 2 of x squared minus 2x equals 3. I'm going to change it to exponent form. 2 to the third equals x squared minus 2x. 2 to the third is 8. If I subtract 8 from both sides, 0 equals x squared minus 2x minus 8. Factor that. I need them to multiply together to be negative 8, add together to be negative 2. That would be x minus 4 and x plus 2, which means my two solutions would be x equals 4 and x equals negative 2. Again, going back up to the original problem, you can't have the log of a negative number, so x equals 4 is my only solution.